Okay, so let's see, organometallic compounds. So organometallic compounds are extremely important in organic chemistry. They're widely used. They have a lot of useful reactions that they can do. A lot of them are highly reactive. A lot of them can be made to be enantioselective using chiral versions or chiral catalysts. So they're really important in organic chemistry. So if we look at sort of the nature of organometallic compounds to figure out what their reactivity is, what we'll notice right away is that we have a carbon bonded to a metal. Metals are not very electronegative. So in this case, we get a partial minus on the carbon and a partial plus on the metal. Hopefully you recognize this is unusual. We either see carbon without a partial charge if it's bonded to another carbon or hydrogen, or it has a partial positive charge. So if we look at alkyl halides, carbon-bromine bond, the partial minus is on the halogen, partial plus is on the carbon. Carbon-oxygen bond, same thing. Carbon-nitrogen bond, same thing. Carbon bonded to most things we see is either neutral or partially positively charged carbon. And so that's what's immediately unique about organometallic compounds is we now have carbon with a partial minus charge. And what that does then is it has it act more as a carbon nucleophile. And so far, we've really only seen carbon act as an electrophile. Now, that's not completely true. We did see 2 carbon nucleophiles, CN minus, that's got a lone pair on the carbon atom. So that's obviously a nucleophilic form of carbon. And then acetylide ions. But other than those two, typically we've seen carbon with a partial positive charge and therefore serving as an electrophile. But again, with organometallic reagents, that polarity is reversed, and now carbon is the nucleophilic atom. The metal is partially positively charged. Okay, so a way that we can assess just how basic and nucleophilic the organometallic carbon is, we can estimate this based on the percent ionic character. And what that means is for these bonds that are covalent, how polar covalent are they? Are they closer to non-polar covalent, or are they way on the other side and closer to almost fully ionic? And the more ionic something is, the more negative charge you're going to have on that carbon, because the closer it is to actually being a carbon minus and this other plus cation. And the closer it is to covalent, then the less nucleophilic and basic that carbon is going to be. So the way we can assess the percent ionic character is to look at the electronegativity difference between carbon and these other and these different metals. So the carbon-lithium bond has an electronegativity difference of 1.5. That's 60% ionic character, and this is by far our most reactive organometallics out of the ones that you're seeing down here. The ones that we're going to use in this class are going to be these 3. All of these can form, and there's actually, this is not even an exhaustive list. There's tons of other organometallics you can form as well. The 3 we'll go over in 30B are these 3 right here. So the carbon lithium organometallics are the most reactive, then the carbon with the magnesium, followed by carbon with copper. And so you get a sense by looking at the electronegativity difference and the corresponding percent ionic character, you get a sense for how reactive these things are, or how nucleophilic and basic the carbon atom is in these compounds. So it's the most reactive in organolithiums, second most in organomagnesium compounds, and then it's the least reactive in carbon-copper bonds. So again, as we go down with the smaller difference in electronegativity, we have more of a covalent bond than we do an ionic bond, and so it's not quite as reactive. But I will point out that even carbon-lithium bond is right there on the cusp. It's not fully ionic, but it's quite close. Let's see. So organometallic reagents behave like carbon nucleophiles. They behave like carbon anions. So that's what I was saying before. We don't draw them as anions because none of these are fully ionic according to their electronegativity differences, but they react similar to that. So let's first draw the partial charges on these so we can get a sense for what the partial charges look like. Here, bromine is going to be partial minus. Here, oxygen partial minus. Here, carbon is partial minus due to the fact that lithium is partial plus. And again, just based on electronegativity differences. Here, each carbon is partial positive, one more than the other, but and then finally on the top one, carbon again is positive. So what this is meant to show in all of these cases that we've seen before, in most cases we've seen before, the carbon is the thing with the partial positive, And now it's the thing with the partial negative. So that's different. So that means alkyl halides are carbon electrophiles. Epoxides are also carbon electrophiles, but now organometallic carbons are carbon nucleophiles. So this is pretty significant. As far as the arrow pushing for these, the way that we want to show these, instead of drawing it like a carbanion, since they're not technically fully ionic, we don't want to draw it like this. But if you look at this form, you can pretty readily see how you might draw it. You're going to have the lone pair go to the electrophile. But since we don't draw it as an ionic pair like we do here, instead we want to come from the carbon-lithium bond. That's where the electrons are. They lie closer to carbon than they do to lithium, but they're still in that covalent, polar covalent carbon-lithium bond. So when we draw a carbon organometallic acting as a nucleophile, the electron pair is going to start, or the arrow is going to start on the electrons in the carbon metal bond. So they're going to start here and then hit your electrophile. You don't have to write the plus Li plus, but I just want to pretend it still exists, so I'm drawing it there. Okay, so here, like I said at the table, the larger the difference in electronegativity, the more reactive the organometallic is going to be. And hybridization and resonance are also going to affect the reactivity. So any factors that stabilize anions will make them, the anion itself, less reactive. Okay, that's what I have up here. So, similar idea to what we looked at with acid-base chemistry. If you made the base form of something more stable, it was a weaker base, but it also made the corresponding acid stronger. So things that stabilize the negative charge on the carbon are going to be less reactive organometallic reagents, less nucleophilic, less basic, and things that if it doesn't get stabilized, then it's going to be stronger. Okay, so when we're trying to think about which organometallic is more or less reactive than another, one thing we can look at is the nature of the metal. We already covered this, right? The bigger the electronegativity difference, all other things equal, the bigger the electronegativity difference between carbon and the metal, then the more reactive it's going to be. The smaller that gap, the less reactive it's going to be. So that is what we're looking at for this first set here. Because if we look at the carbon attached, so if you want to think about, so let's just imagine these as carbanions for a second, because they do sort of behave that way. If we can argue that something about the structure stabilizes a carbanion, then that would be a less reactive organometallic. If we argue that something about the structure we're looking at compared to some other structure destabilizes it, then we would predict that that is a more reactive organometallic reagent. So this is sort of similar to what we did with acids and bases, where we said the more stable the conjugate base, the stronger its corresponding acid. And so we looked at how things stabilized or destabilized the conjugate base. But here we're looking at the base directly. We don't have to think about its conjugate acid. So here it'll be a little more straightforward, and just that the more stable we argue that that thing is, then the less reactive it is. If it's less stable, it's more reactive. So we don't have to do the weird thing we do with acids where we say, oh, this is more stable, so on the other side it's more reactive. So we don't have to do that part of it. Okay, so the first one is just the metal. I'll answer this one for you. The organometallic that's most reactive here is going to be the organolithium, because that's the one with the largest electronegativity difference, just based on the table I gave you above. Okay, so now let's look at the next one. And I don't know if I just forgot to delete this from your notes. If you actually have these plus charges up here, or if they're just annotated versions of what I mistakenly left in. If they're left in your notes, make sure you know that that's not what we're actually comparing here. But the reason I had these in is when I was teaching this the last time, what I did is I said, well, because people had a little trouble kind of determining how stable an anion was. And I said, well, okay, well, how about what stabilizes a cation? Anything that stabilizes a cation should destabilize an anion, right? Anything that you argue it provides stability to a plus charge should do exactly the opposite to a negative charge, because plus charges are looking for things to donate in and help stabilize them. So if you have things that can donate more electron density to something, great for a plus charge, exactly the opposite what you want for a minus charge. So I don't know if you find that helpful. I found that when I drew this out like this, so let's just imagine them as anions. people weren't entirely clear on what exactly the issue was that we were kind of comparing here with reference to stability. So I said, well, imagine these three are all cations. Which one would be the most stabilized? That's going to be the least stabilized anion. So A, B, or C, which would be the most stabilized cation? So just cation, which is not really the question here, but let's start with the cation. Which one is most stabilized? Okay, great, C. So then by default, C is then the least stable anion, the most reactive anion. So here what happened was with our plus charge, we got hyperconjugative donation from the adjacent carbon-hydrogen bonds, right? So that hyperconjugation effect stabilized that cation. So that hyperconjugation effect still exists, only now it's not going to serve to stabilize things, it's going to destabilize the anion. So just think about this in terms of cation stability. The more substituted, the more stable. It's going to be exact opposite for anion. If more carbon groups is more electron donating, and an anion already has negative charge, that's the last thing we want in terms of stability. But it's exactly what we want in terms of reactivity. I can tell you that. So lack of stability can be a great thing. Lack of stability of certain functional groups and certain just certain ways we do reactions are what give us the ability to perform these reactions. If everything was stable, nothing would react with each other, and we wouldn't be able to build up these compounds. In fact, this compound here is so reactive that if you have a syringe of it in lab, they usually are packaged up in these, what's called a SureSeal bottle, where everything's stored under argon or liquid nitrogen. Then there's a seal put over it. And then there's like a wax layer put over that. And then you open it up, you put in a nitrogen line, you put in your syringe, and you pull it out. And you can do it in such a way that everything is transferred in a completely atmosphere-free environment, so that it doesn't come into contact with oxygen in the air, which sometimes can react with reagents. And it also can't come into contact with moisture in the air or water. And so these SureSeal bottles can allow you for that. If you were to take a syringe full of butyl lithium, or tert-butyl lithium, this is called, tert-butyl lithium. If you were to take it out of the bottle and just hold it there, not even squeeze anything out, just pull it out open to atmosphere, you'll see sparks out of the tip of your syringe without even expelling any of it. You just pull it out of the bottle, you will see sparks from the butyl lithium that's at the very tip of the syringe. And if you squirt it out, which you would just like absolutely not do, it's extremely dangerous, you would see it just shooting flames out the tip of the syringe. It's extraordinarily reactive. On the other hand, if you take butyl lithium, which is the linear version of this, I still wouldn't recommend shooting it out the end of a syringe barrel, but you'll see it fizzle, but it's not going to cause a huge fire, at least not on a small scale. So there's a really, really enormous difference in the reactivity based on how many carbon groups are attached. So don't do any of that with butyl lithium, especially not tert-butyl lithium, but just to try and impress upon you the reactivity of these things, and also just the reactivity of these organometallics and organolithiums in general. I mean, that's a pretty reactive species where you can just pull a syringe of it out and it just starts flaming out of nowhere just from a little bit of water in the atmosphere. So these are extraordinarily powerful reagents. So when we say this is unstable, yeah, that's true, but that's a good thing. If we need a really, really strong base, like a super mega base, this is it. If you need things that are really, really reactive, these organolithiums can provide a lot of good reactivity that you might want. Okay, so what are we looking at? Most reactive. Okay, so A was the most reactive here. C is the most reactive here. Let's take a look at A, B, and C. What do we think for these? Which one is the most reactive, which means which anion is the least stabilized by some effect? So which of these is the most reactive? And remember that hybridization puts S character sits closer to the nucleus. So it can better stabilize an anion if you have more S character, because that anion will be held closer to the positively charged nucleus. So the most stabilized thing up here is C, but that means it's the least reactive. right? So if you imagine these as carbanions, which would look like this, this, and this, and then you remember what the different hybrid orbitals look like. We've got sp, sp2, sp3. We have an anion here, or an anion here, or an anion here. The one that's going to be most stabilized is the one that's much closer to the nucleus. The one that's least stabilized is going to be the one that's farthest from the nucleus. So the sp3 hybridized one, which is B, this is going to be the most reactive. Most reactive here. I can, you know what, I'll also do least reactive. So you have this for your reference, reactive. So the least reactive on the top is going to be this due to electronegativity difference, the least reactive. And the second one is going to be this because it's primary versus secondary versus tertiary. The least reactive in this one would be the one with the most S character. And then the least, the least reactive, most S character, most reactive, least S character. Okay, and then the last one. Okay, so the last one, what are we looking at here? We're basically looking at, did I mean to change this one? No, maybe I meant it to be tricky. No, because I'm asking for the most reactive. Okay, this one's actually, I don't know if I made a typo here, but this anion here, if you draw it as the anion, the one in the middle, it's going to be resonance stabilized. So that is going to be our least reactive, most stable. And then A and C, neither of these have resonance stabilization one way or the other. And this alkene out here doesn't really do anything significant. So these two would both be most reactive. One might be a little bit more or less reactive than the other, but it's not going to be by a huge amount. Okay, organolithiums and Grignard. So organolithium and Grignard reagents. So Grignard reagent, let me define what that is because I'm not sure if I use the term. Grignard reagents are just the organometallics, the organomagnesium organometallic compounds. So I'm going to show you how to make both of these here. And I'll tell you right now that for the most part, these organolithiums and Grignard reagents, they do many of the same reactions. They have many of the same reactions in common. Because they're somewhat similar in the reactivity. Organolithiums are a little more reactive, but Grignards are a very close second. So you'll find throughout the rest of the course that most things that organolithium can do, the Grignard reagent can also do. That's not true for every reaction. There are some things organolithium does that's a little unique, but for the most part, they're often interchangeable. But again, there are a couple things that you can only do with lithium, and we'll see one of them here today. Okay, so with the organolithium, what we're doing is we take the halogen, and we are going to exchange it. We're basically going to exchange it with the lithium. So here, we're just swapping out the halogen for the lithium. And for the mechanism, we're going to come back to this because I don't want to spend too much time on mechanisms that I know I'm not going to test you on and that are very different from other mechanisms we've seen. I'd rather get through the material so that you're prepared to do a bunch of practice problems and then come back and fill in these other pieces of information later, rather than have you be prepared with this stuff later in the week closer to the exam date. Rather, the sooner I get the important stuff out of the way, then we can fill in the gaps for this other stuff. Okay, so with Grignard reagents, it's a similar reaction. We reacted with magnesium metal, but because magnesium, if you look at the periodic table, lithium is in group 1, so its oxidation state is +1. And so carbon being the -1 in this case, it's already charged balanced. With magnesium, magnesium is in the second group, so it's +2. So the carbon only gives it 1 of what it wants. And so the other thing you get is the bromine atom just attaching on the other side. So here magnesium is a +2 state, the carbon gives us a -1, the other bromine gives us a -1. That's what charge balances the magnesium. So the fact that you have just lithium versus Mg and Br in the second one just has to do with the oxidation state of those two. Is Grignard specifically engineered? Specifically magnesium. Yeah. As far as the specific reference to Grignards, yeah, it's always magnesium. And then same thing here, we'll come back to this mechanism, very similar to the lithium one, nothing too crazy. Something that I want to point out about these reactions is that if you use an alkyl halide that has EZ geometry, that EZ geometry is going to be preserved. So here I did two alkyl halides that don't have alkene, so obviously they don't have EZ geometry. But here's an example of what I mean. Because there's no limitation on the kind of alkyl halides in terms of the carbon atom it's attached. The carbon atom attached can be sp3, it can be sp2. In theory, it could be sp. I think you'll see most commonly sp3 and sp2. But in the event that we have an alkene attached like this, you'll see in the reactant, we have a geometry of the methyl groups that cis to one another. I'm gonna fill in the mechanism later. And so when we react this with lithium, those methyl groups stay cis. So we don't scramble it, we don't invert it in any way, we keep it exactly the way it is. So that's important to keep in mind when you draw these reactions out. So if we generate the organometallic from an alkene, vinyl, I guess I should say, alkyl halide, any relative geometry about that alkene is going to be maintained. Okay, something to be aware of when we work with these organometallic reagents, something I keep warning you about over and over, always be mindful and aware of potential acid-base reactions. I feel like this is around the point when people start to believe me when I say that, because now there's just been like back to back to back issues of like not considering acid bases and what that can do. So usually it's about this point that people are finally convinced that they really need to consider acid base stuff. It's particularly important to consider it when you're working with organometallics, because these are extraordinarily strong bases. I mean, I told you that tert-butyl lithium is so strongly basic that it just turns into, you know, flames shooting out the tip of your syringe just from pulling it out of the bottle. And that's because it's so basic that it's just like grabbing any water in the atmosphere that it can react with to undergo an acid-base reaction. So you do not want to do these reactions in the presence of an acidic proton. So we'll have to define exactly what that is, and that will define the scope of functional groups that will be allowed to be present if we're using an organometallic. So if we react this with water, we're going to get an acid-base reaction. We get this plus hydroxide. If we react this with water, we're going to get the same thing, acid-base reaction. And OH minus. The equilibrium constant for these, hopefully this will be now even more convincing why we can't have acidic protons such as OH groups around when we have organometallic reagents. The pKa of this is 50. The pKa of this is 15. That is a 10 to the 35th power in favor of the product side. So you have no evidence of any organolithium or any Grignard at that stage. 10 to the 35th power is you basically have 0 molecules of reactant. So that's an extraordinarily favorable acid-base reaction. It's going to happen rapidly, and it's not going to be reversible. Okay, so now the question is, clearly we can't have OH group around. That's a massively favorable acid-base reaction. So if you have an OH group around, you don't want that if you're going to use an alkyl or organometallic, because it's going to immediately undergo an acid-base reaction. So what about these other ones? Well, let's just sketch in their pKa. So the pKa for this one is 35, 25, 15, 15, 7 to 8, let's say 8, 5. Can we have any of these around with an organolithium? Nope, not a single one, right? The conjugate acid of the organometallic when it reacts is this here. And the pKa of this is 50. 50 is a higher pKa than every single pKa on this list. So we cannot have any of these functional groups around unless they're the thing we want to react with. If we want to do that acid-base reaction, then by all means, that's great. We can do that acid-base reaction. But if you're intending this organometallic to serve as a nucleophile somewhere, but in the meantime, you've got all these things that can react with it in an acid-base fashion, and remember, acid-base reactions are super fast, then these are going to be problematic. And that brings us into the things we can and can't prepare with organometallic reagents. And this just has to do with functional group incompatibilities. So let's take a look at what those are. Actually, you know what? Let's come back to those. Yeah, let's come back to those. So we'll fill in the mechanisms next time. We'll fill in this issue of incompatibility next time. I think for right now, let's just recall that you shouldn't have acidic protons anywhere near an organometallic reagent, because if you do, it's going to react with it. And that might mean an organometallic around some other compound that has an acidic proton, or it may mean the concept of making an organometallic out of something that has an acidic proton. Let me just go over the first one just to address this right away, because it's not actually that detailed. We'll go over the last two later on. I can't make an organometallic reagent out of this, because on one side, I'm going to have this extremely strong base, and on the other side, I've got an acidic proton. So the exact mechanism of how that's going to destroy itself, we can work on next time, but we can't make that. You can't have a super base on one side with an acidic proton on the other side. It's going to react with itself. Okay, so now let's talk about the reactions that these electrophiles actually, the reactions that these organometallic reagents can do. One of the really cool reactions they can do is react with epoxides. And what's cool about that, or why don't you tell me? I actually have a question in the notes. What is so great about this reaction? Does anyone want to tell me what's so great about this reaction? Now go ahead and draw the arrow pushing while somebody tells me why this is just such an amazing reaction. And also, while you think about that, an organometallic, I told you, is a really strong base. So obviously, if we react these with epoxides, that's going to be under basic conditions. And so it's going to attack or open the epoxide at the less substituted position. And then we'll have to have an H3O plus work up later. So if we do this arrow pushing, why don't we start here? Nobody wants to tell me why the reaction is so great. Why don't we start with A, B, or C? What is going to be the product of this reaction? Okay, great. Yeah, it's going to be C. Yep, so if we open that up, after the H3O plus workup protonates the O minus from the epoxide, we're going to get this. So can we now tell me what's so great about the reaction? What kind of bond did we form here? We formed a new carbon-carbon bond. We don't know many of those reactions. And in fact, until right now, we only knew one. I guess if we went over acetylide last time, technically we knew two. So far we know an acetylide reacting with an alkyl halide. You might want to make a note of these. It's important to keep these in mind. Carbon-carbon bond forming reactions, acetylide reacting with an alkyl halide, acetylide reacting with an epoxide, organometallic reacting with an epoxide. So now we have three. And we're going to have a fourth in just a little bit here, actually. But so far there's three. So we want to make sure we know what those are. Because remember, when we see in a synthesis, we formed a new carbon-carbon bond, we immediately want to think about what carbon-carbon bond forming reactions we have available to us. Up until, last Friday, the answer was pretty easy because it was always acetylide ion. 100% of the time, it was the only carbon-carbon bond forming reaction we knew, so it had to be acetylide. So now that question is getting a little more complicated, but nonetheless, we have this many carbon-carbon bond forming reactions and this many reactions of everything else. So it still does very much narrow down the pool of reactions you could be selecting from once you recognize that you're forming a new carbon-carbon bond. And then what you do is you kind of think out, what are those carbon-carbon bond forming reactions? What do they look like? And what does the stuff I'm dealing with look most similar to? Which reactivity pattern does that kind of match up with the most easily? So it gets a little more complicated now when to have more carbon-carbon bond forming reactions, but it's still a much more limited number of reactions than the other reactions as a whole. Stereochemistry. So stereochemistry, we don't have any stereochemistry here because we are not forming any new chiral centers and we didn't start with any chiral centers, so there's no inversion to show or anything like that. But if there was stereochemistry to show, it would be because the side of the epoxide that you were opening was a chiral center, and you would show SN2 inversion if you had that. We don't have it here though. So let's do the mechanism, which I basically already did up here, but that's okay, I'll do it again. So step one, we are going to react the organometallic with the less substituted side of the epoxide. Then we get this. Let me just make sure I counted carbons properly. 1, 2, 3, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4. Okay, I'm good. And then you go to the workup step, which is part 2. So if you're running this lab, you're letting the organometallic and your epoxide, you're going to let them stir around for a few hours. And there are ways of checking the progress of this first part of the reaction, but it's not really something we talk about in this lecture course. We'll talk about that in my lab course. There are ways you can monitor that, but once you're sure that those two are done reacting and all of this has been completely converted to this, that's when you go to the H3O plus workup. Because if you go to the H3O plus workup while you still have a bunch of unreacted organometallic and unreacted epoxide, you're going to get an acid-base reaction immediately with your organometallic. That's going to quench it. It's no longer going to be reactive. And there's no longer any reaction with the epoxide that you could undergo either. So you always want to make sure that those two are done reacting completely, and then you can go to your H3O plus workup. So now we protonate this, and that's how we get to this product here. Okay, so you would think though that since acetylide anions can react with both alkyl halides and epoxides, that organolithiums or Grignard reagents should also be able to react with alkyl halides and epoxides. We have seen them react with epoxides, we just did that, but unfortunately they do not react with alkyl halides. And this again speaks to just how strongly reactive some of these organometallics are. So when we're dealing with alkyl halides, typically what we say is primaries with a strong nucleophile or base is going to undergo SN2. Secondaries, now it matters if it's a strong base or a strong nucleophile. For secondaries to do SN2, it needs to be a strong nucleophile but a weak base, right? And then tertiary we go from there. But the point here is that at least with primaries like acetylide ions, we would imagine that since acetylide ions can react by SN2 with primary alkyl halides, which is common for strong nucleophiles and primaries, the organolithium would allow that as well. But it turns out here, organolithium and Grignard reagents are so strongly basic that they defy even the rules of typical alkyl halide reactions, in that you are going to actually get an E2 reaction here, even though that's a primary alkyl halide. So something you have to keep in mind is those rules for, predicting substitution elimination of alkyl halides. They're meant to predict the most common reactions of alkyl halides. So you don't want to extend them to things outside of alkyl halides, but you also can't 100% limit yourself to every reaction of an alkyl halide has to follow these rules. That's within the scope of most things that are strongly basic. They'll still undergo SN2 if it's primary. But here, those rules of substitution elimination and which pathway to achieve or you're going to get in those reactions, it just doesn't account for something so wildly basic like organolithiums or Grignard reagents. And so they defy even the rules of substitution elimination we learned with alkyl halides. And even here, even with a primary, we end up getting E2 just because they're so strongly basic. So don't do this. Do not react RLI with RBr. And I'll put in parentheses SN2. It's not going to happen. But there is a workaround here. The workaround is organocuprate. So I thought I had a mention of this. Yeah, here it is. This is where cuprates come in handy. So cuprates were down lower on the list of things that are much less reactive as organometallics. You could, if you wanted the E2, that would be fine. Yeah, that would, I guess, sort of be a workaround to using something like terbutoxide on a primary. You could use something like that, but it would have to be, that would give E2 as well. So you could view the fact that cuprates have a much lower difference in electronegativity and then being less reactive, you could view that as a disadvantage. But I don't think it is. I don't think something being extra super reactive or super unreactive is an advantage one way or the other. It really just depends on what you're dealing with. If you're dealing with a really stubborn functional group that you can't get to react with anything else, having this incredibly powerful base like terbutyl lithium or these incredibly powerful alkyl lithium nucleophiles is great. But let's say instead you have something that is can easily react with things, but it's got other sensitive functional groups around that might be able to react as well. In those cases, you might want a more toned down thing. So along with a decrease in reactivity comes an increase in selectivity, right? Something that's super reactive isn't selective. It'll react with you and you and you and you and you and you and anything it sees. If you tone down the reactivity, you lose out on, what the scope of what it can react with. But that also gives you something that's more selective. It says, oh, I only react with these two things, but I don't react with this and this and this and this and this. That could be good if I don't want to react with all those other things. So it just depends on what you're dealing with. Sometimes the reactivity is the thing you want. Sometimes the selectivity or lower reactivity is the thing you want. So it depends on the exact scenario that you find yourself in. What are these? All right, this is similar to, this is more of the question we already did above, and then there's which one cannot be made. That's more of the thing I said I would address next time. It's basically more of this, which one can we not make and why? So we'll get there. Looks like we have a quick picture of Casey tucked in here, taking up all the pillows and the corner of the couch too, I might add. So it's like one of those, couches that fits into the corner and everybody wants the corner spot, and Casey is in the mix as well. And she usually, well, if I'm in the room, she usually gets it. If I'm in the room, she gets whatever she wants. If more sane people are in the room, that might be different. But I mean, look how comfortable she is. You're gonna make that dog move? And it's insane. I'm not gonna move that. That's perfection right there. Okay, organocuprates. So this is what I was just talking about. Organocuprates are far less reactive than the organolithium counterparts, but that can be a good thing if you don't want something so aggressive. You want something that's a little more selective, or that aggressiveness up here led us to not being able to do SN2, which typically we can do in a primary alkyl halide, but lithiums are so aggressively basic that they can't do that. And that's where the cuprates come in and can be a solution to this. Cuprates can actually do SN2s on primaries. Cuprates can actually do SN2s on secondary alkyl halides as well. So that's actually an advantage over alkynes, because alkynes or acetylide ions are typically such strong bases that we can only do those reactions with primary alkyl halides. If we want a secondary type reaction, we would have to do some sort of like an epoxide opening there. But cuprates, however, can do this SN2 reaction on both primary and secondary alkyl halides. And to make cuprates, it's a two-step process. The first step is you make you prepare an organolithium. You take that and you react it with copper iodide, and that makes your cuprate. So what a cuprate looks like is a copper atom with two of your alkyl groups on it. So here, whatever organolithium you're dealing with. And then it's a minus charge on copper, and there's a lithium plus counter ion. So don't worry too much about the fact that the structure of these looks a little bit different from the other organometallics, but again, it's a difference in oxidation state. Lithium was +1, so it's just alkyl and then lithium. Magnesium is +2, so it's alkyl, magnesium, bromine. And then copper is yet a different oxidation state, so you end up with two of your alkyl groups and then a lithium plus cation. Let's see. Okay, geometry here, let me go ahead and address this. For these reactions, if you start with an organolithium with a particular EZ geometry on it, that's going to be preserved when you make the cuprate. So if you think about it like this, if we started from this alkyl halide, remember that when we make the organometallic, the geometry is preserved. So if I react this with lithium, I get this. And now if I react the lithium to form a cuprate, I now preserve that geometry yet again. And so it translates the whole way through from the alkyl halide to the organolithium to the cuprate. And then whatever this cuprate is transferred onto, it maintains that geometry there. So once you have that geometry, it's going to translate the whole way through your reaction sequence, even down to when the cuprate itself reacts. Okay, so the reactions, cuprates, okay, so cuprates reacts with epoxides in the same way as Grignards and organolithiums. So that's just another version of a nucleophile we can add. We saw it react with organolithiums and Grignards. Epoxides can also react with cuprates. So all three of those are good for epoxides. But what sets cuprates apart is that they can actually react with alkyl halides, not just epoxides. And so that gives us yet another way to form a new carbon-carbon bond. So this is the last carbon-carbon bond we're going to form, at least until after we do spectroscopy. So now we can add that to the list. We have, if you want to make sure you have all these down, acetylide reacts with primary alkyl halide, acetylide reacting with an epoxide. What was that last one? Organometallic reacting with an epoxide, and now cuprate reacting with an alkyl halide. And they can be primary, secondary, and there's actually an even broader scope here. So this is a really, this is a reaction that's extremely broad in scope. So not only can we do primary and secondary alkyl, whereas alkynes could only do primary, and organolithiums and Grignards could do none of them. Not only do we get substitution with primary and secondary alkyl, no tertiary, however, we can also get substitution on vinyl halides, allyl halides, aryl halides. We were never able to do SM1 or SN2 on vinyl or aryl before. So that is a brand new mode of reactivity. So here, we can transfer this alkyl group onto this carbon. It doesn't undergo an SN2 mechanism for the the vinyl and the aryl, because you can't do SN2 on an sp2 hybridized carbon. However, it does do a substitution just by a very different mechanism. I believe I have it on here somewhere. I think it's pre-written out. Where is it? I swear it was on here somewhere. Yeah, down here. So I'll talk about this next time, but this shows you the mechanism for these cuprate couplings. It undergoes something called oxidative addition, reductive elimination, and we'll take a look at those next time. Okay, so what we're doing is we're basically transferring one of these alkyl groups. So even though there's two on that cuprate, only one of them reacts. It actually turns out once the first one gets transferred onto something, then the cuprate itself with that one alkyl group that's left over is actually dead. It doesn't do anything. But we are going to attach this onto the position where we had the bromine, and we're going to attach it at this carbon. So the carbon attached to the metal is the one that's going to swap out for that bromine. So the product of this reaction looks like this. Here again, we're going to attach this carbon here, the one attached to the copper. It's now going to attach itself to the one attached to the halogen. Use a different color for this one. Oops. I drew the product wrong. So that's what's good about highlighting those carbons and actually mapping them out, because you can very quickly see if you messed up the problem like I just did. So red goes to green, and then there's this. There we go. So the same thing up here. Red here, green, green, red. Okay, let's do the next one. Red, green. So I'm marking the carbon attached to the halogen, and the carbon attached to the metal. So now I'm going to attach red and green. So red is here. Green is here. And then I have to account for this last methyl. Which way do I want the methyl group to point? Up or down? Remember, all these geometries transfer. So what you want to do is you want to look at the place where you see the EZ or cis trans geometry in the reactant, which in this case would be the cuprate, and then look at the geometry about that cuprate. So let's look at the geometry of the methyl compared to the bond to copper. So this copper lithium as a group. Is the copper and the methyl cis or trans? Yeah, it's trans. So here's my alkene. The cuprate is pointed up off of that. The methyl is pointed down off of that. So those are trans, which means they need to, that bond needs to remain trans in the product, which means it's got to go down this way. So this was, let's see, this bond here was the bond to copper. And so that bond needs to remain trans to the methyl group that's pointed down. Okay, so carbenes. If you look at the structure of a carbene, so the carbene basically has two bonds to it and then one lone pair of electrons. Do we think this, what is just your gut instinct? Is this a nucleophile or an electrophile if you look at this carbene? Yeah, don't think too hard. Just what do you see? You see that? What does it look like? Yeah, it looks like a nucleophile to me. It's not at all. And if we look a little closer, we can see why that is. But I think at first sight, this screams nucleophile to me, right? Because I see a lone pair of electrons, that looks like a nucleophile. But these intermediates are quite weird. You can have carbenes that are more on the nucleophilic side than electrophilic side, but I think a classic carbene is much more of an electrophile, even though your immediate gut instinct is to say that's a nucleophile because you see the lone pair of electrons. But if we look a little more closely and we look at what's going on with carbon in terms of how many electrons it's surrounded by, it's only surrounded by a total of 6 electrons. So there's 2 in this bond, 2 here, and 2 here. So this has an incomplete octet. Normally, the time we see a carbon with an incomplete octet is when it has a positive charge, when it's a carbocation. When it has a carbocation, it's got also 6 electrons, but 2 of those electrons are in, or all 6, I should say, of those electrons are in bonds. And in the carbene, only 4 of the electrons are in bonds. The other pair of electrons belongs all to carbon. And that's why it doesn't have a plus formal charge. If you just do the formal charge calculation for this, which says you take the number of valence electrons it should have, which is 4. Carbon goes to group 4 in the periodic table. And then it's got 2 bonds and 2 lone electrons. So what we do is subtract the number of bonds, which here is 2, plus the number of lone electrons, which is 2, and that gives us a formal charge of 0. So the structure is a little misleading if we don't think about what the formal charge is and the fact that it has an incomplete octet on it. But even though it has 0 formal charge, it has an incomplete octet, which means it's highly electron deficient. So despite the fact that it looks like a nucleophile, it's actually quite electron deficient. So we are going to look at a couple ways to generate carbenes. Carbenes are basically going to be a nice way of making 3-membered rings with all carbon atoms. So the general mode of reactivity that we're going to see for carbenes is that they're going to react with alkenes. In essentially an electrophilic addition type reaction, the alkene is going to serve as the nucleophile to initially attack the carbene carbon, and then the electrons on the carbene carbon are going to come back down, and we're going to form a 3-membered ring. So this looks a lot like the formation of epoxide rings, only now it's going to be all carbon, there's no oxygen in it. The nice thing about this is because this carbene reaction is concerted and works very similarly to epoxidation, all the stereochemical considerations that we've considered for working with epoxides are all going to apply to form these cyclopropane rings. So the stereochemistry will look identical to epoxides. So now it's just a question of how we make these carbenes, and it looks like I already have the mechanism written down here. I'm going to just erase it so I can redraw it to show you guys. Yeah, the heat or light is needed for this reaction. So in this case, what we're doing is we're taking something that is highly unstable and is really close to forming a carbene, and we heat it up ever so slightly, and we're going to see what happens to generate that carbene. So CH2N2, this is diazomethane. And the structure of that looks like this. There are two resonance structures for this. I'm going to draw both of them. So this is one resonance structure for diazomethane. Another resonance structure for diazomethane would look like this. And we get here. So there is a really, 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 really good leaving group on here, and that is N2. So this is an extraordinarily good leaving group. Nitrogen gas is all over the atmosphere. It's pretty stable on its own as N2, looking like this. And so if N2 is a gas, there's first of all a huge entropy that could be gained from breaking that off and allowing it to be a gas. So there's a huge entropic component to that anytime you form a gas. And the other thing about this is we know nitrogen gas is actually used pretty commonly to run reactions in the lab under an inert atmosphere. If you need something super, super inert, you usually use something like argon or one of the noble gases. But just from day to day, for day-to-day purposes, oftentimes people will use nitrogen gas, and in almost all undergraduate labs that require these kind of inert atmospheres, we use nitrogen gas because it's a lot cheaper than argon. So nitrogen gas is not completely inert, but it is fairly inert. And when I say it's fairly inert, that means it's also extremely stable. And so it would be a really, really good leaving group if you kicked it off. And particularly now because this nitrogen in this resonance form has a positive charge on it. So that is an extraordinarily good leaving group. It's such a good leaving group that this is one of the most dangerous chemicals that you could possibly work with. You usually will not be able to buy diazomethane. You usually have to make this in the lab yourself, which is brave, I'll say, at the very least. So the reason you can't buy diazomethane is it's referred to as a chemical that's shock sensitive. And shock sensitive means that if you agitate it in some way, drop the bottle, shake the bottle, the bottle gets a little bit too warm, any of that kind of stuff, what happens is it will explode. It will literally just explode completely. And the reason for that is because you basically have this extremely good leaving group bottled up in there. And if you drop the bottle or shake the bottle or it hits a rough surface on the inside of the bottle, it's just enough energy to get that leaving group to leave. And if you have a gas building up rapidly inside of a bottle from that reaction happening, it's going to blow the nitrogen gas out and explode. And so you can't typically buy bottles of this because nobody's going to want to drive the truck across the country to ship this chemical to you and have their truck explode. Right? So it's not something that you can very easily ship. And it's actually so explosive that in the laboratory itself, if you want to make and use diazomethane, normally what we do is we have reaction flasks that are going to have these ground glass joints at the top. And it's so that when you fit different stoppers on top of it, it makes a really nice seal. But the problem with the ground glass joints is that it's a rough surface, and if the diazomethane touches it, it will explode. And so you actually have to use completely specialized glassware that doesn't have any ground glass joints anywhere. You have to make sure it's really clean and there aren't any, dust particles or anything else on the surface, because it's just extraordinarily sensitive to anything that could set it off and have that nitrogen gas leave. So not something you have to worry about on paper, but it is a very, very powerful reagent. But when you do it, you can, if you heat it just ever so slightly, you can get this nitrogen to actually act as a leaving group. And then what you're going to form is this. And this is our carbene. So this carbene is then capable of reacting with alkene. So if we mix this alkene up with diazomethane, heat it up a little bit, the nitrogen gas leaves, and then it can react with the alkene. And again, the way in which it reacts is the alkene is going to act as the nucleophile. And then the carbene carbonate is going to come back down and form the bond on this side. That step of the carbene reacting with the alkene is concerted, which means it's going to be a syn addition. And this is a meso compound, so we're not going to form the enantiomer, but that's what our product looks like. So again, these are going to look exactly like what we do when we react with epoxides. We just don't have an oxygen there, but all the stereochemical considerations are going to be identical. So that is one way to make a carbene. There are other ways to make carbenes. This way is going to be a little bit different in that, well, the mechanism is different, but also the actual structure of the carbene is going to be different. Here, we're going to end up with 2 halogen atoms on it. So CHCl3 is chloroform. If you take chloroform and you react it with a strong base, specifically terbutoxide, and the reason we use terbutoxide as opposed to some other bases, we can get other weird things happening if we use a less hindered base. Okay, so let's go ahead and pull this proton off. Oops, negative charge. So the first thing we're going to do is form this anion. You know, that first step is very similar to what we saw with diazomethane, only is the bottom arrow pointing to the bond of the carbon. The bottom arrow.
Sorry, in the last reaction on the third step,
yeah,
with the lone pair, is that arrow pointing to the carbon or is it pointing to the bond, or does it matter?
Yeah, it does matter. So I'm starting off at the pi bond. I don't know if this is the arrow, but I'll just show both again. Here I'm starting off at the pi bond because it's the pi electrons that are reacting here. And that's landing on the carbon atom. And then the pair of electrons on the carbon is then pointing at a carbon. So I think I see why you think these arrows are confusing. What you have to remember is when we did reactions with alkenes and like HCl or something like this, we started from the pi bond and we landed on a hydrogen. And that first arrow didn't actually tell us which carbon atom got the hydrogen. We just had to deduce which one got the hydrogen based on where the resulting carbocation would be more stable. And that would be that the carbon on the end here is the one that got the hydrogen. And that's just simply implied in that next step, because we'll draw a cation at one position, that must mean the hydrogen went to the other position. And so it's a similar thing happening here. I'm using the pi electrons here and landing them on carbon, but I'm not saying which carbon atom actually formed the bond to that carbon. Here, it doesn't matter which one. And so it's just presumed that whichever one I don't draw that second arrow to must be the one that got the original bond to carbon. And so if I draw this second arrow coming here down to the carbon, then it's presumed based on that arrow that this carbon got the carbene carbon originally. So that sort of makes sense.
Yeah, that makes sense. Thank you.
Yeah, and it's similar to it's actually the same thing we saw with the reaction of Br2. I do realize why they look confusing. We had the pi electrons come here to bromine, and then we had bromine come back down. And so having the bromine lone pair come back down to this carbon here must mean that the original point of attachment to the bromine was that one up there. Can we attach as much as on the carbon? So can we make dashes and wedges on the carbons? The carbon is attached to. You can't have a combination of dashes and wedges because it's a syn addition. But you could either do both dashes or both wedges, because this one is a meso compound. It doesn't matter which one you choose, but you don't want to do a combination of both because of it being a syn addition.
I was saying not the dashes that are coming off the carbon. I was saying what it's attached to on the.
Oh yeah, you can do that. So the chiral center is here, and so you're allowed to make any of the four bonds there be dashes or wedges. So the general convention is that you can have two that are in the plane, one that's forward and one that's back. It's that even then that's not the only way to do it, but that's the most common way you should do it. And so, yeah, in this case, you could make the three-membered ring part in the plane, and you could make these rings either dashed, ring bonds, either dashed or wedge. Yeah, that would work. Okay, so now we are really close to generating the carbene. Like I said, this is really similar to what we saw with diazomethane just a minute ago. We didn't do an acid-base reaction to form an anion. We rather just looked at one of the other resonance structures, which had an anion. But now we've done something similar with this bottom one, only we had to actually deprotonate it to get it. But now the next step is going to be the same, just like with diazomethane, where we had a leaving group leave once we have that anion on carbon. We're going to do the same thing here. So we can have the chlorine group leave. And we're going to form a carbene that way. And then the rest is going to be the same as we saw before. So now that we have this dichlorocarbene, we're now going to react with our alkene. And get this. Okay, and then there is a third way that we can make carbenes, and this last one is called a Simmons-Smith reaction. I don't know if you guys have the two on yours or not. But this is, so this is yet another way to make a carbene. This one is a little different in that the reaction that we're doing here actually forms something called a carbenoid. That OID ending basically means it's not exactly that thing that we're referring to, but it reacts like that thing, meaning we don't form an actual carbene, but we form something that reacts like a carbene. So that's what's meant by carbenoid for these kinds of reactions. So with these ones, we're using CH2I2, which is diiodomethane or methylene iodide. And we're going to react that with a zinc copper alloy. And what that's going to do is form a structure that reacts very similarly to a carbene, but is not an actual carbene structure. Okay, so let's take a look at this one. So the first step for this, we're going to do something, oops. So our CH2I2 is going to react with the zinc, the zinc copper alloy. And it's going to do something that's called oxidative addition. It's not something you have to worry about mechanistically for this class, but it is the mechanism by which I was referring to last time, telling you that the cuprates react by that kind of mechanism. They do an oxidative addition reaction, and then they do a reductive elimination, and that's how some of the cuprates react with alkyl halides. With normal primary and secondary, they may just react by SN2, but the other ones do that sort of oxidative addition kind of reaction. So when we do oxidative addition with CH2I2 into the zinc, then what we get is this. We get a zinc atom, iodine here, and then CH. Oops, one of those should be hydrogen. So we're basically inserting, let me draw out the full structure of CH2I2. So we're basically inserting the zinc atom into this bond right here. So the zinc is going to go right into the middle of that carbon iodine bond, and then you're forming a bond to a new bond between zinc and iodine and zinc and carbon. So it's basically just scooping out that bond and just inserting itself right between that carbon iodide bond. And so from here, what we have is this structure here, and this structure remains looking like this. But if you try and understand using arrow pushing why this reacts like a carbene, because looking at this structure, I don't think it's so obvious why this is a carbenoid or why it would react like a carbene. But if you break down the general idea behind organometallics, and this is not the mechanism by which anything is occurring, but just separately down here, I'm going to take a look at what we could think about in terms of how this thing is reacting. Remember that organometallics are such that you have a partial minus charge on the carbon, which is unique about organometallics. Normally your carbon is partially positively charged. So you think of that as sort of a carbanion, where you have a negative charge on a lone pair of carbon. So if we simply draw it out like that, even though again, this is not the correct structure because it is a covalent bond. But if you think about it in terms of the reactivity, just like any other organometallic reagent, you essentially have a minus charge on carbon, and then you have your positively charged metal that it's attached to. So if you kind of just break that open and take a look at the reactivity mode that you're thinking about here, even if this doesn't actually happen, you can then get a sense for how this thing would form a carbene or react at least like a carbene. And here, just like with the other two carbene reactions, first we generated an anion carbon, then we had a leaving group leave. Here we still have one good leaving group, which is iodine. And so then you can imagine how this has reactivity like a carbene, even though these things don't happen down here. So this stuff does not actually happen, but again, it just gives you a nice way to see how this thing might behave like a carbene, even if it doesn't actually fully form a carbene. And so then the way that we use this in an arrow pushing mechanism is we take our alkene, and then we're going to react that with our carbenoid. I'm just going to draw like this, zinc, iodine. You can have the alkene react with the carbon atom, the one that's acting like a carbenoid. So just like we would with any other carbenoid reaction, we're going to have the nucleophilic alkene react with the electrophilic carbenoid carbon. And then from there, the electrons in that carbon zinc bond are going to be the ones that come back down. So again, this is actually very similar to what we saw with the reaction of an outright carbene. We just don't have that full carbene structure sitting there. Oh, sorry, I forgot to kick off my leaving group. Okay, and that's going to give us this, which again is a meso compound. Yeah, exactly, and that's all in one step. So it's basically combining all the other steps of the carbene reaction. So before, what we did is we formed an anion, kicked off a leaving group to form the carbene. So that was 2 steps: form anion, kick off a leaving group to form carbene, and then do the electrophilic addition reaction with the carbene and the alkene. So here we're having the pi bond directly react with the carbenoid carbon, kick off the leaving group, and then have the electrons in the carbon zinc bond come back down. So yeah, this is all one step. There is a first step of this oxidative addition of zinc into the carbon iodide bond, but once you form that happens all in one step. Okay, so now we have a few practice problems for these. Again, the stereochemistry is identical to epoxidation, so there's nothing new here about this. Anything that we would do with respect to forming an epoxide using an alkene, we're going to follow the same standards here for the carbenes. So down here, our carbene is going to be the one with 2 chlorines on it. So just like we did with epoxides, I think the best way to draw these out, again, not the only way to do it, but in my opinion, the best way to draw these out to make sure you get the stereochemistry correct is form your carbene or your three-membered ring, cyclopropane ring, put that in the plane just like we did with epoxide rings in the plane, and then make your substituents either forward or back based on the relative stereochemistry of the starting material. So here I'm going to make my 3-membered ring in the plane. I'm going to add my chlorine atoms at the top so I don't forget them. And then if I look at the starting material across the pi bond, I had 2 ethyl groups that were trans to one another. And so I'm going to maintain that here. So I'm going to put 1 forward and 1 back. And then I'll get the enantiomer of that. Okay, let's look at the next reaction. Here we're doing CHCl3 again, so we're going to get that dichlorocarbene structure. And now I essentially have the same starting materials before, only I'm starting off with the cis isomer rather than the trans. So in this one, I'm going to form both of the ethyl groups in the same direction, which means this one now is a meso compound, so we don't have an enantiomer to draw. Okay, the next one is diazomethane. So this one is just adding the CH2 group to make the cyclopropane ring without chlorines on it. So I'm going to do the same thing I did before. I'm going to put the 3-membered ring in the plane. And then I'm going to look at the relative geometry of the substituents in the alkene starting material and then fill in the stereochemistry accordingly. So let's see here. The ethyl and the methyl on each side are cis to one another. So if I make this one forward with the ethyl, then I also want to make the methyl group over here forward. And then I'm going to have an ethyl back. And then I need to form the enantiomer of that. So that will be where the ethyl over here is back. The methyl is also back. And then the other ethyl is forward. What happens to the zinc is sort of the same things that happens when you react an organometallic reagent in general. So if you think about what we did with epoxide openings with an organometallic. So let's take our CH3 MgBr. So if we were doing arrow pushing for this, I would have done something like this. And sometimes I just kind of ignore it. In this particular case, what happens is I have an anion on oxygen, which means very likely that's going to be paired with the MgBr cation that's up here. If we look at the Simmons-Smith reaction, the ion pair you would get out of this one would be, you would basically get zinc diiodide out of it. So when you do this arrow pushing here, you're kicking off an iodide atom here. And then by using these electrons in the carbon-zinc bond, then they no longer belong to zinc anymore. Carbon took them along with it to form that bond to the alkene, which means I'm then kicking off ZnI plus. So Zn plus with one iodine. And then down here in this step, I kicked off I minus. So I'm going to couple the I minus anion with the Zn iodide plus cation, and then I'm going to get zinc diiodide neutral. So just using the electrons in the carbon-zinc bond to form a new bond and knowing that those electrons belong to carbon and not to zinc, that's how you rationalize where the zinc is going. It's just going to separate out and ion pair with whatever else is in there. Okay. Okay, yeah, so I think I'm just going to skip these mechanisms entirely. They're just not super important. So don't worry about those. But let's definitely address the limitations because that's extremely important. So we have limitations on the types of organometallic reagents that we can make. They're really useful intermediates, and they're really reactive, and they undergo a lot of good reactions that can help us make new carbon-carbon bonds in particular. But we also have to be very mindful of the things that they can interact with that we might not want them to interact with. And so one of those concepts is you do not want organometallic reagents around acidic protons unless you want them to react with that acidic proton. Generally, you make organometallics to react with something else, but that's not exclusively true. So you may want an acid-base reaction to occur. But something you have to be mindful of, so if you want to make an organometallic that you can react with an epoxide or react with an alkyl halide or react with something else to form a new carbon-carbon bond, you want to make sure there are no acidic protons around. Because remember the section I had just before what I'm about to fill in down here is that these are extraordinarily strong bases. And so if you think about what kinds of protons would these organometallics be able to react with, it's nearly everything on our pKa table, because nearly everything on our pKa table had a conjugate acid with a pKa that was lower than that of the conjugate acid for the organometallic reagents we're dealing with, which means all of these would be a favorable acid-base reaction with an organolithium or an organometallic, just more generally speaking. Because again, the pKa of the organometallic reagent is somewhere above 40. And so all of these would be favorable acid-base reactions, which means you cannot make an organometallic reagent out of something that contains any one of these groups. And you cannot react it with something that contains any one of these groups, because the first thing it will do is that acid-base reaction. So again, if you want the acid-base reaction with the organometallic to occur, then it's going to work quite well. But if you're trying to react it with something else other than a hydrogen, then you need to be really careful of that. So a thing I couldn't react an organometallic with, let me just go ahead and put that off to the side. I can't react this with something like this, because the first thing that's going to happen is the organometallic reagent is going to go after that acidic proton and deprotonate it. That simple acid-base reaction is always going to be faster than any other reaction, such as an epoxide opening or any other reaction that the organometallic reagent can do. There is a slight workaround for something like this, which is you could just add an excess of your organometallic reagent. So if you just say, okay, that's fine, I'll let it deprotonate over here, and then I'll just add excess of the organometallic, so then there's enough to also react here. So that's a possibility, though you do have to be careful of that. One thing you have to be careful of is if you, had some really elaborate organometallic reagent that you made, you won't want to use an excess of it just to prevent an acid-base reaction. That's going to be a problematic situation there. Yes, exactly. That's the solution for this one. So one solution is to use excess, which isn't always a great solution because, like I said, if you spend more than one synthetic step making this organometallic reagent, the last thing you want to do is waste half of it on an acid-base reaction that you don't even care about. So one solution, yes, is exactly that. We can use a protecting group here to protect our alcohol before we react with the organometallic. And then the other thing I wanted to remind you of, in terms of if you want to just use an excess, while you may not want to waste your organometallic, another thing you have to be careful of is when I do this acid-base reaction and form this O-, is there going to be something that O- can react with that I don't want to happen? And if there is, then you definitely need to use a protecting group here. So that's one issue. We don't want acidic protons around if we want to react with an organometallic reagent. So we can either use a protecting group or use an excess if that's appropriate and there's not another side reaction that can occur. And then there is the issue of making an organometallic reagent out of something that has an acidic proton on it or has something that an organometallic can react with. And that's an issue too, because here, if I try and make this organometallic reagent, even though this reaction might not happen intramolecularly, it can happen intermolecularly. So we have like this. I'm just going to draw another molecule of itself. So this can act as a base to deprotonate another molecule of itself. And so that reaction is going to propagate on until it's all done deprotonating itself. And in the end, what you're going to have is just a big pot of this. You're basically going to have the propoxide anion, and that's all you're going to be left with. You're going to protonate this carbon on the end, so the lithium is going to be gone. There's going to be a hydrogen in its place. That's right here, and then all of your OH is going to be deprotonated as O-. And then, of course, you'd have your lithium plus counterion here. So you can't make an organometallic reagent out of that. It's just going to react with itself very rapidly, and it's not going to be able to exist at all. You also can't, here the protecting group strategy doesn't always work. The protecting group strategy for making your organometallic reagent, for this one, it might work. What you really want to be careful of is you do not want to use a protecting group on the beta position of your organometallic. So beta to your lithium atom. So your alpha carbon being the one that lithium is attached to, the beta position is the next one out. And that's because this can do sort of an internal E2 elimination reaction. Is oxygen a good leaving group? No, not particularly, but you have essentially an anion on carbon when you have an organometallic reagent. That's a much stronger base than an anion on oxygen. And so this is still a highly favorable elimination reaction. Because you're essentially, even though it's technically a covalent bond, you're essentially exchanging a negative charge on carbon for a negative charge on oxygen. So oxygen is not normally a good leaving group in this way, but if you compare it to a negative charge on carbon, it's better to have negative charge on oxygen than carbon. So you end up getting an internal like beta elimination reaction here. So you don't want to do something like that. So you definitely don't want any sort of oxygen atom or any other potential leaving group beta to your organometallic reagent. So this is not a good solution. Protecting group works okay here, not a particularly good solution down here. Another thing you can't make an organometallic out of is something that contains an electrophile, right? Organometallic reagents react with electrophiles because they're nucleophiles. And so that's another limitation here. I'm going to get rid of the carbonyl for the time being. It is, in fact, you cannot have a carbonyl there because they are electrophilic. But since we haven't covered carbonyl chemistry yet, I'm going to actually switch this to a different group, which is an an epoxide ring. Because this we know reacts with organometallics. Organometallics also react with carbonyls. We just haven't covered that yet. So I don't want to go and show you something that we don't understand the reaction for it yet. But I guess I'll leave it up in the sense that don't have carbonyls in your reaction with organometallics. So I'll go ahead and leave it up there and just say don't do it. But we'll find out later why. So again, another one we can't do is something that has an electrophilic atom in it. Because if we form this, make sure I have the right number of carbons. 1, 2, 1, 2, 3, 4, 1, 2, 3. Oops, missing one. We then have a nucleophilic carbon on one end of this thing. And then we have an electrophilic carbon on the other end of this thing. So similarly, this is going to start to react with itself. So unless that's the intention, then you don't want to do something like this. So here again, it could be intramolecular, where this one just reaches over and directly reacts with it. Or it could be intermolecular, where we just have two different molecules. We never have just one single molecule of this in our reaction flask, but we have a flask full of molecules. So one end of the organolithium for one molecule is going to react with the epoxide end of another one. And again, it's just going to destroy itself. So these kinds of molecules that I'm showing here are just going to self-destruct the second you make them. So we can't really avoid that. And there's no protecting group we can use for an epoxide. There is no protecting group for something like that. So there's nothing we can really do to avoid it. There is a workaround here for something like this, though. If you want an epoxide, just add it in later, right? You can use this as your organometallic to have it do whatever you want to do. And whenever it's done forming the bond you want to form, then you can just later react that with MCPDA. So this is an issue. While there's no protecting group for an epoxide, you can easily overcome the reactivity or the incompatibility issue by just installing the epoxide later on in your synthesis. If you have it as an alkene that doesn't react with organometallics, and alkenes can easily form the epoxide later. So that's a very solvable problem. And then finally, here's just another example of an acidic proton. Remember, all of these protons up here can be readily deprotonated by an organometallic reagent. So we don't want to have them around while we're trying to either make or use that organometallic. And this gets people into trouble, I think, because people commonly try to use something like this. So I'm gonna point this out right away and say, don't do it, don't do it, don't do it, because people hate epoxides. I know you guys hate epoxides. Everyone hates epoxides for some reason. They don't like them. And so they go out of their way to avoid using an epoxide. The problem here is that oftentimes what they'll do is try and make something like this, right? Because this ultimately is sort of like a substitute for an epoxide. We've got a nucleophilic atom on one side, and then we have a protected oxygen group on the other side, but it's that 2-carbon piece we're adding. So people will often try and use something like this in place of using an epoxide, and it just doesn't work. So don't do something like this. It's just going to eliminate to form these two things. That's not going to work. So typically what we can do in place of something like this is just use an epoxide in our synthesis rather than try and use some sort of protected organometallic reagent. I believe we had a similar issue. Did I already cover both of those? Okay, limitations on organometallics. Did I have another section here for limitations? Oh yeah, right here. I knew there was another one. Yeah. The last limitation was a double. Yeah, exactly. The last one is just going to eliminate itself off and just form ethylene gas. Okay, so which of these cannot be made? So what do we think here? Let's just start with A and B. Can either one of those not be made between A and B? Or both? So which one can't be made, A, B, or both? Yeah, great. So we don't want to make something like this. That one can't be made. It's going to deprotonate itself. Nothing wrong with A. What about between A and B in the next pair? Or both? Okay, Again, B. B has an electrophilic epoxide, a nucleophilic organometallic carbon. So that one can't be made. And this one's fine. Okay, how about between these two? Which one can't be made? Can both not be made, or none? You can answer none as well if you want. Okay, great. A can't be made. Organolithiums don't actually react with react with alkyl halides to do SN2, but they can react to do E2 elimination. So these also can't be made. And this one's okay. And then let me just add one more. Which one cannot be made? A, B, none, or both? Which ones cannot be made? A, B, none, both. Okay, I'm glad people are saying A, because I want to make sure you don't use this attempted workaround for epoxides, which is just going to undergo elimination on itself as soon as it's formed, to form something like this. And then with the, which is now not a nucleophile at all. And B is actually okay here because of the fact that it's now not a terminal alkyne. It doesn't have that acidic proton on it. So in this case, there's nothing that can eliminate out. And the alkyne is not in and of itself the problem with organometallic reagents. It's the fact that if you have a terminal alkyne, that proton is acidic, and therefore that introduces the problem. So it's not the alkyne itself that's the problem, it's acidic protons on alkyne.